Guys, did we say that carbon dioxide in previous chapters? We said carbon dioxide, I think it was chapter 5, is not polar, although it has got two polar bonds, but these two bonds are pulling electron away from carbon on exactly opposite side with equal pull. So this compound is nonpolar. Remember, we showed nonpolar by writing mu. By writing mu is 0. That means dipole moment is 0. There is no negative end or positive end in carbon dioxide. It's not polar. Not polar. This means not polar. However, carbon dioxide solidifies. Have you seen dry ice? Dry ice is solid carbon dioxide. Solid CO2, which is dry ice. If it is if it solidifies, it means there must be some form of interaction. Otherwise, it would have stayed as gas or liquid. And this is what we think is happening. What do we think is happening? My slides are jumping today again. So this force is called London dispersion forces. We still don't understand that. But the explanation, the hypothesis is that in carbon dioxide, although there is no polarity, but can I say there are protons in the nucleus and protons in the nucleus. And when we have molecules coming closer together, these protons are going to pull the electrons of another carbon dioxide toward the proton. So more gathering of electron on one side, that means the other side becomes short of electrons, so partial positive charge. And this partial positive charge is going to pull the electrons from the third molecule closer to partial charge, partial positive charge. So the other end becomes positive. So this definition is saying that there is instantaneous interaction between induced polarized molecules. So this interaction, this positive and negative, is result of induction. So we call them induced polarity. When molecules get together, they push electrons to opposite side or to one side. So there is partial positive negative because of change of distribution of electron clouds. And we call this induced polarity. So this induced polarity is producing some interaction which results to solidification of carbon dioxide. This interaction is very small. That's why carbon dioxide sublimes at minus 78 degrees of Celsius, very low temperature. At 1 atmosphere, carbon dioxide goes from solid to gas at minus 78 degrees of Celsius. So because London dispersion forces are extremely weak forces between molecules. Do you remember we also talked about methane? Do you remember we said methane is nonpolar? It has tetrahedral, none of the bonds of CH, 4 CH bond, none of them are polar. We said this is also nonpolar. However, there are some moons and planets where they see, it's so cold, they see the snow of methane gas. That means methane gas can be solidified. That means although methane is nonpolar, it can have London dispersion forces. And we now believe London dispersion forces exist between all sorts of molecules. Is the London dispersion forces in ionic compound? Is the London dispersion forces in covalent compound? Is the London dispersion forces in hydrogen bonded compound? They all have London dispersion forces. Except in nonpolar compound, that is the only force which exists.
London dispersion forces are only found in nonpolar compounds?
No, it is going to be observed in polar as well.
Oh, okay.
But they are only, so if I talk about a polar molecule, it could have hydrogen bonding, it can have dipole-dipole, also London dispersion forces. But if we talk about CO2, which is nonpolar, it only has London dispersion forces.
Oh, so CO2 won't have hydrogen or the other
That's
three.
right. And that's right, yes. So guys, if I use this concept, if my logic is valid, is it fair to say that ionic compound, because they have a stronger ion-ion interaction, they must have higher melting point? And if I have hydrogen bonding, the melting point should be higher from simple dipole-dipole interaction. And if I have London dispersion forces, the interaction should be even weaker. That means lower melting point. So this is actual experimental evidence. Look at these 4 compounds, they're all ionic. And look at their melting point, above 801 degrees of Celsius, very high temperature to melt them. Why? Because they have a strong ion-ion forces between molecules, between units. And if I look at these 4 compounds, and they all have hydrogen bonding, do you see generally their melting point is very low, much lower than ionic compound. 0, minus 78 for ammonia, minus 98 for CH3OH. And if I move from hydrogen bonding to dipole-dipole interaction, which is much weaker force than hydrogen bonding, these are the 2 examples. They do not have hydrogen bonding. However, the 2 molecules are polar, so they make dipole-dipole interaction. Look, the melting point is still going lower from previous categories. It starts from minus 123, it goes minus 142. And if I compare the 3rd class with the 4th class of compounds, which are nonpolar, look, there is dispersion forces. The melting point is still lower than dipole-dipole interaction. So these are an indication, these are the proof that the stronger force between molecules is ion-ion, hydrogen bonding is weaker, dipole is still weaker, and the weakest interaction is dispersion forces. So that's how we explain melting point of different substances. Why are they too high? Why are they too low? How much energy we need to go from solid to liquid?
So is an ionic bond the same as the iron bond? Is it the same thing? Or have you been saying ionic the whole time?
Are you talking about ion or iron?
Yeah.
Which one? Upper
one
or lower one?
I'm talking about both, but I'm meaning, were you saying an ionic bond or an iron bond?
No, ion bond. I-O-N,
Yes.
not I-R-O-N. I-R-O-N is not any of this. The bond in iron is not any of this. They are called metallic bond, and we haven't talked about them yet.
Got you. Okay, thank you.
You're welcome. I'm glad you asked.
Sorry.
No, not at all. So guys, go ahead. Can I ask you to use what you just learned to explain and decide these compounds, what sort of forces do you see between these units? Go, guys. Thank you, Victoria. Good job. So let's do this together. Guys, if I look at BR and BR, look at BR and BR. Is this polar or non-polar? Is this molecule polar or non-polar? BR and BR. The bond between two identical atoms, is it polar or non-polar?
Is it non-polar?
Yes, they have same electronegativity. And if it is non-polar, which one of these forces were only observed in non-polar? Which one of 1, 2, 3, 4?
That's dispersion, right?
Good job. Yes, so this is 4, right? If I look at D, KCl, is it ionic or covalent?
How do we tell for that one?
See, metal and non-metal. Potassium is a metal.
Oh.
Metal and non-metal usually make ionic compound. It is ionic, so it must be ionic forces, right? Forces. If I look at water, do you remember what type of forces in water?
That's hydrogen bonded with an oxygen, so that's the hydrogen bonding.
Yes. If hydrogen is sitting on oxygen and nitrogen, do they make hydrogen bonding?
Yes.
So that's 3.
Now, if I had a covalent bond, like if I had
This is covalent bond.
Oh, nitrogen and hydrogen is?
Yeah.
Because they're that's because they're both non-metals, right?
Good job. Yes.
Okay.
And if I ask you guys, is NCl3 non-polar or polar? We know it's covalent. And if you write the Lewis structure, you're going to get a pyramidal structure. It looks like this. Is the bond between nitrogen and chlorine polar or non-polar? What is electronegativity of nitrogen, guys? Is it 3.0? Somebody would check it for me. I think chlorine is 3.0. How about nitrogen?
Yeah, I'm pretty sure they're the same.
Okay, thank you. So can I say the bond between these two is non-polar, right? There is no difference between 3.0 and 3.0. So you don't have a polar bond. However, you have lone pair. You remember we said when you have lone pair, the electron cloud is not symmetrical. There is more cloud at this end than the other end. So if you have non-polar bond, you see a little bit accumulation of electron density on the upper part. So that's usually lone pair result of tiny electron pool vector. They behave like it's an electron pool vector. So you have a slight polarity. That means this is polar. And what was the force between polar molecules which don't have hydrogen bonding? Is it number 2, dipole-dipole? If I go to next slide, these are the correct answers. So that's how you analyze these questions. You look at one at a time. Separate the polars and non-polars first. Separate the ionic from covalent bond first. Then on the polar ones, see if they have hydrogen bonding or not. Any questions, guys? All right.